My guest today is Professor Dong Lai, who is Professor of Astronomy at Cornell University. His research interests include astrophysics of neutron stars, black holes, white dwarfs, exoplanets, and astrophysical fluid dynamics. Welcome, Dong.
Thank you very much, Gio. It's a great pleasure to be here.
Yeah, so thanks for doing this. So our discussion today is going to be a little bit technical, but really interesting. So I want to start with one of your older papers from 2014, Chaotic Dynamics of Stellar Spin in Binaries and the Production of Misaligned Hot Jupiters. You said many exoplanetary systems containing hot Jupiters are observed to have highly misaligned orbital axes related to the stellar spin axes. So before we get into the details of this, so hot Jupiters are our own Jupiter-like planets, but they are much closer to the star. Is that what a hot Jupiter is?
Indeed, right. Hot Jupiter are the extrasolar giant planets, so Jupiter-like planets, but they are orbiting other stars. And as you said, the orbital period, they're very close to a host star. So the typical orbital periods like 1 or 2 days, a few days, 1 to 5 days, instead of years. Okay, right? So it's very close. So that was one of the great surprises in astronomy over the last several decades. It's a great discovery, and in the late 1990s, right? So that's indeed a hot Jupiter. It's a puzzle, basically.
So what's the orbital period of our own Jupiter?
10 years, 10 to 15 years, that kind of thing. I should know the number, but it's years, tens of years.
The many years. And we have Jupiter-like planets orbiting other stars, but they orbit really fast, like within a few days.
Indeed, that's immediately give you quite a surprising result, right? When first discovered in the late 1990s, it was quite surprising, and so the immediate question is how they are formed. How do you get them to form so close to their host star? Right, it's a very puzzling result, right? And it was a complete surprising result. So the general thinking is that based on our understanding of how planets are formed, is that they must have formed very far away from their host star at very large distance, like our own Jupiter from the sun, right? But somehow after they formed, they migrated through some kind of dynamical processes. They migrate from far away of the host star to the inner vicinity of the star, to be very close to the star, right? So that's the general idea. Now, exactly how they migrate, it's a question that's still being debated in the community.
Yeah. So I don't know much about this, Dong. So Jupiter is a gas giant. So if Jupiter were very close to our own sun, wouldn't that have an effect on the gases, and would it actually start losing the gas? Is that
good question? Somewhat, but not completely. I mean, indeed, if you put our own Jupiter at the very close distance from our own sun, the Jupiter will begin to lose mass slowly, but not completely. It's not going to lose. The mass will not be gone. Basically, we'll lose a little bit mass. Indeed,
little bit of mass.
Yeah. So they can still survive. They can still survive. But the question is the formation. It's very hard to imagine how you can, because when you put this thing so close to the star, everything's so hot. It's baking. The radiation it's very hot. So how do you make things condense? Out of this. Initially, the way we think about planet formation is that initially you basically have a gas and dusty disk around the star, right? Then somehow you need to lump them together, produce lumps, and then coagulate, right? So that's relatively easy to do at far away distance because it's cold, right? Yeah. Right. But when you put them so close to the sun, it's so hot already. How can you make them lump out of this? It's very difficult. So that's why the general thinking, more or less consensus, is that these giant planets they were formed very far away from their host star, right? and then through some dynamical processes, they migrate inwards to their current very close location.
Very close
Okay.
to. Okay. So going back to the paper, this is about sort of the misalignment.
Okay.
Right. So could you define what you mean by sort of the so
Okay.
what's the spin of the sun? How do you
Okay. So let me. This is another surprise. Like now in the solar system, everything is very ordered, right? The sun is at the center. It's spinning around its axis. There's the spin axis, right?
Yeah.
Spin axis. Now all the other planets, it's orbiting around it. They're the orbital axis. Each planet has orbital angular momentum axis, right? So, I don't know, right? So the spin axis of sun, the orbital axis of the planets. The
So
orbital axis is perpendicular to the plane,
so the
right?
sun is like a top spinning, so you
Indeed,
can actually determine the axis,
indeed,
and then the things around it, we can determine sort of the plane of that, right?
right. The axis is perpendicular to that plane. Okay.
Yeah.
Now in the solar system, all these axes are more or less aligned, right? The sun's spin axis, the planet's orbital axis, they're all more or less similar. Now, if you a picture of the solar system, it's very ordered. Everything is in the plane. The sun's equator is also in the same plane, right? All the axes are actually aligned within 7 degrees, not completely. They are
7 degrees. Yeah.
7 degrees. I mean, not a big deal. I mean, there's a few degrees, right? Okay. Okay, so they're more or less aligned. So in the solar system, the sun's spin axis is aligned with the planet's orbital axis within a few degrees. So everything's very ordered. So that's consistent with the general notion of our general understanding of how planets and stars are formed, right? Because if you think that I mentioned briefly before, right, the basic notion of star and planet formation is that you have basically a proto sun, right? They're spinning and then they're surrounded by a disky, dusty disk material, right? And everything is sort of rotating in the same sense, same direction. So you form a planet out of that disk, the orbital plane will be the same plane. So it makes sense that everything is ordered. So that's what we find in the solar system. Now, for the hot Jupiter system, right? This misalignment is a big discovery. It's a big surprise, big surprising finding. Namely, very often you find that some of the hot Jupiter system, they have their host star, the parent star, is spinning one direction, but the orbit is in different direction. Right? Sometimes they are opposite, what we call retrograde. So meaning that the star has a top, right? The stellar is like this, right, spinning, but the planet's orbit is sort of opposite way. So it's completely different, from what you envision what the solar system will be like.
Yeah. So is that symptomatic of what you were talking about before? Is that symptomatic of the fact that these planets formed elsewhere that migrated toward the star?
Well, okay, so I haven't told you what's the way or how do you migrate yet. I'm just telling you the puzzle, right? The puzzle is, right, first of all, you have this planet so close to the star. That's already a puzzle. The second puzzle is these planets often have an orbit completely different direction from the spin axis of the host star, right? So the question, how do you get such a thing? Okay, how do you migrate? How you form a planet far away migrate, and how do you get this misaligned configuration? Right? So that's okay. So that's a question. So one appealing solution, one possible appealing solution, it's what we call high eccentricity migration. So let me describe that, right? So what happens is that, okay, so initially you have a Jupiter far away from their host star, large distance, a few, just current location, right, very far away, right? And it's moving in the same direction as the host star. It's ordered right now. Initially, immediately after their formation, everything's ordered. Now imagine you have a distant companion.
Yeah.
this whole star has a planet, but you have a neighboring star,
Right.
what we call a binary star. So binary star is not unusual in astronomy in the galaxy. In fact, more than 50% of the stars are in binaries. Our sun happened to not be in a binary system, but many other stars actually come in pairs. Okay, so binary. So again, the picture is we have a star with a giant planets, cold Jupiter, in the normal, newly formed happy configuration. But now imagine you have a faraway companion, stellar companion. Okay. Now what happens is that even though this companion is very far away, the gravitational force from that companion star is going to act on the orbit of these planets.
Yeah.
It's going to make the orbit become very eccentric. So the orbit is no longer circular. So it's elongated, very elongated, like the comet. If you think about comet, right, in the solar system, the comet, they come from far away, and they come, very close to the sun, and then you go back to far away places and come back. So that's called eccentric orbit. So what I'm saying here is that this companion star, even though it's very far away, its gravitational force acting over time, if you accumulate over time, can change the orbit shape of the planets in such a way that the orbit become very eccentric, such that it can come very close, because it's very eccentric means that it can come very close to the whole star. Right? Okay, and then once it becomes very close to the star, then you can imagine some dissipation process, some frictional force can circularize it.
So the host star sort of captures it.
Exactly. Yeah, that's another way to put it. Yeah, indeed. Right? Because when they're far away, the planet's far away from the host star, you cannot capture it. But when it come very close to it, then you can imagine some dissipated process, friction, that kind of thing, dynamical process. Then you can sort of capture it and make the orbit shrink. And then that's how this thing works.
The companion doesn't have to be a star. It could be a neutron star. It could be other objects also.
Yeah, could be a neutron star, could be other objects, but most likely it's another star because, as I said, binary stars are quite common. Binary star could be quite common. Could be another planets, distant planets, right? There could be another planets. It's also possible, right?
And so this process of binary systems, essentially pushing something to a sort of an elongated orbit and then ultimately captured by the host star. So at that point, are you saying, Dong, that we don't really have any predictions as to what those orbital planes might, how they will align with the host star?
Okay, so here it's the thing, right? So when it when this distant star, the distant star, companion star, does not have to be aligned with the original orbit, right? So you have this, again, the parent star, the planet, they're in one plane. The host star can be in very different direction, in different plane. So when they push the orbit of the planet into elongated orbit, they also change the orientation of the orbit.
Yeah.
They can also change the orientation, the orbital inclination of the orbit. Okay, and so you can imagine now. So now from this, you can imagine now that basically, because of this distant host star, it actually changed. This distant host star actually does two things. First, it makes the orbit elongated, allowing the parent star to capture the planets. Second, it actually changed the orientation of the orbit. The original orbit plane of the planet is in one direction, but because of the gravity of this other distant companion star, it actually changed the orientation of the thing, of the planet star. Okay, so you can imagine. So we start out with an ordered planetary system, right? But because of this very far away companion, you would think it's not important, but over time, remember, the time helps us in astronomy. You have a lot of time. Millions of years, billions of years. The gravity over time, acting over time, they change the orbital orientation, and then that you begin to have this non-trivial misaligned configuration.
So is that the leading hypothesis? So if there's a binary star of sufficient mass and interacting with, something that is with the host stars, planets, if there's a binary star of sufficient mass, over time it could basically completely misalign the current system.
Mm-hmm.
Is that the leading hypothesis? Are there other ways, other possibilities?
Oh, there are other possibilities. So the other possibility, okay, the other possibility of migrating this thing is just, for example, you form this giant planet far away, but the gas around the star is still there.
Yeah.
Right? Remember the initial condition, the way we think about how planet form is that you have a star surrounded by dusty disks. Out of the dust disk, you form this lump of planets, right? Now you form this planet you still have disk around it. Then you can imagine the planet moving in the disk, right? When it's moving in the disk, it's going to experience friction, just like when you have tennis ball moving in the air. It's experiencing friction, so it's going to slow down. So what happens here is that, again, you have a planet moving in the disk. It's going to experiencing drag force, so it's gradually spiraling in the disk.
Yeah.
Spiraling closer and closer to the star. Okay, though eventually, of course, will be very close. But then you can imagine that the problem. How do you stop it? How do you maybe get eaten up by the star, right? And this also has a problem. How do you, in this picture, everything will still be ordered, right? You will not get this misalignment, right? Because you can imagine, this thing initially is everything in the same plane. The star is rotating in the same direction. So migrating, you're gonna get an aligned system.
Yeah.
It's not gonna so this hypothesis, this we call disk-driven migration, it's possible to explain this migration process, but it's very difficult to explain this misalignment process.
Right.
Why it's misaligned? It's actually quite difficult in this picture, right? Yeah. So that's why many of us like this other way. Basically, you form this planet, the planet is happy sitting there, and then over a long time, because you have a giant companion, very far away stellar companion, through the gravity of the companion, they can do this, pushing the planet into eccentric orbit, elongated orbit, and at the same time, change the orbital orientation, and therefore producing this misaligned configuration that we see today.
So
that was
so two questions, Dong. So since we don't find much misalignment in the solar system, can we reasonably assume that there is no big thing out there that we haven't seen yet?
Excellent question, indeed. Indeed, that may be our solar system is very ordered, right? So they don't have this hot Jupiter. Also don't, so it's indeed hot Jupiter is not very common. Happens around 5% of the stars. So our solar system is not one of them. It's not one of them. So indeed, so that may be, basically, you need a sufficient nearby companion to do this kind of things, right?
Okay.
And
also, right? So I was wondering. I obviously don't know anything about it. Jupiter is obviously a much smaller body compared to the Sun.
Indeed.
But the sort of the Jupiter Sun system, has it had any effect on the Earth, the Mars, and stuff inside? Any sort of orbital fluctuations that we can see?
Oh, indeed, they can indeed affect it. Of course, the gravity from the Jupiter, especially in the earliest stage of the solar system, Jupiter, giant planets, certainly play an important role in shaping the architecture of the solar system.
But we don't see misalignment like we see in this hot Jupiter system.
We don't see that, right? Because that's consistent with the picture, with the isolated picture, where right? In our solar system, basically you have in the earliest stage of the solar system, you just have a rotating star, sun, surrounded by a gaseous dusty disk. And then out of this gaseous dusty disk, you condense out all these different kind of planets, right? And you don't have hot Jupiter, right? Everything is pretty ordered, moving in the same direction, same plane, right? So that is consistent with the general picture. But the hot Jupiter system is indeed unusual, right? And they are not that common, but it's common enough. The 5% of the star have hot Jupiters, right?
Yeah. So, but I was thinking that the Jupiter, our own Jupiter, could be, it's obviously not a very big body compared to the sun, but it has a lot of mass.
Mm-hmm.
And so 7 degrees or so misalignment that we see on bodies inside that system, can that be attributed to Jupiter's effect?
I'm actually not sure the misalignment
So
of what.
you mentioned that it is very, very orderly, but we have, a few degrees of misalignment in the solar system.
Yes. Yeah, the few degree thing, there are many different stories. Yes, we don't quite understand that few degree things. It could be a fluctuation, right? And if you want to ask, what's the origin of that 7-degree misalignment? Why the sun? What I'm talking about here, let me just be more precise since you asked, right? In the solar system, all the planets are in the same plane.
Yeah.
Within 2 degrees. Within 2 degrees. But the sun's spin axis is misaligned with the planet's orbital axis by 7 degrees.
Mm.
So 2 degrees, the plane, all the planets within a plane within 2 degrees, but the sun's equator, rotational equator, it's offset by 7 degrees. Now, if you're asking what's the origin of that 2 degrees, why not 0? If you're asking what's the origin of that 7 degree, why not 0? That's a difficult question. Okay, so the 2 degrees, maybe you can think it just you can't be so perfect, right? They have some mutual perturbation. They're not perfectly, not 2 degrees, very small angle. You think about it, right? Now 7 degrees began to a bit worrisome. Okay, there are kind of different stories about where this 7 degree may come from. Including the most recent suggestion is that maybe Planet 9, some people heard about Planet 9 had played a role in giving rise to, in producing that 7 degree misalignment between the sun's rotation axis and the planet's orbital axis. Again, the story there is that it's similar to what I just talked about, is that Planet 9, even though it's very small mass, it's actually its gravity from the Planet 9 is actually acting on the planet solar system. It's actually gradually has changed the orientation of the planetary system a little bit.
Yeah, I call Planet 9 the revenge of Pluto.
Yes, that's right.
So I want to go to another paper, Dong. So in 2018, you had a paper, Black Hole and Neutron Star Binary Mergers in triple systems.
Yes.
Merger, fraction, and spin-orbit misalignment. So we're not talking about star-planet systems here. So you have a triple system, 2 black holes and a neutron star or something like that?
Yes. Okay, so this is that's a more recent discovery, as some of your audience may have heard. It's in the last few years, the gravitational wave astronomy had become a possibility, had become a reality actually.
Yeah.
By now, as of today, we now have 50 neutron black hole system have been detected. So these are 2 black holes with mass 10, 20, 30, 40 solar mass. They come together, they merge. In that process, they produce gravitational waves. And that gravitational waves have been detected by the laser interferometer gravitational observatory called LIGO, right? And this is a big discovery, was first announced in 2015. By now, as I said, we now have 50 discoveries of this kind of thing, right? Now, This is very exciting, of course, because really it's a new window into the universe. You're finding these black holes are invisible, of course. You cannot see, they don't emit any light, not X-rays, nothing, right? But they do emit gravitational waves, right? And they can be detected, have been detected. Now, so the question is, how do you make this black hole, merging black hole binary? How they come about?
Yeah.
Okay, so I don't know whether I should go back to discuss gravitational wave, that kind of things.
Yeah, we had a little bit about LIGO and the gravitational waves, and so gravitational waves, essentially when large bodies merge, it's a little bit counterintuitive. It could also be almost be called gravitational radiation, isn't it?
It's the same thing, yes, gravitational radiation, yes. So basically when two big mass moving around each other, they radiate gravitational waves. They basically distort the space-time, and that distortion propagate away the ripple of space-time and then propagate to Earth. And then the observatory, LIGO detected, right? And so that was a big discovery, basically.
Yeah.
Okay.
And so in this paper, so you talk about chaotic dynamics of stellar spin in binaries. So what do you mean by that?
But this is other paper. I thought we're talking about. Are we talking? Yeah.
Reading somewhere else. So mergers in triple systems. So
yes.
merger, fraction, and spin orbit.
Yeah. Okay.
Spin orbit misalignment. But these are black holes and neutrons.
Okay. So let me have. Okay, so let me back up a little bit. Okay, so we are doing this. We're discussing this black hole binary now, right? And LIGO have detected. The big question now for the community is to try to understand the origin of these merging black hole binaries. How come you have two black holes, they can come so close together, they can merge? It's not easy, right? Because usually when the two black holes, even if they're in binary, if they're very far away from each other, they don't merge. It will take more than Hubble time for them to merge. In order for them to merge within Hubble time, within the life of the galaxy, life of the system, they have to be sufficiently close to each other. So the big question in our community, for people who care about black hole gravitational wave astronomy, is to try to understand the origin of this merging black hole. How do you bring black holes so close to each other so that they can merge, emitting gravitational waves? Okay, as I said, most binary, okay, so I have backup. Binary, of course, is not, as I just told you before, binary is quite common.
Yeah.
Binary stars. So if you look at the galaxy, there are a lot of binary stars, two massive stars, 20 solar mass, 50 solar mass, they're orbiting each other, right? So if you have this massive star, they will evolve into black hole. That's how we all understand the stellar evolution, the fate of massive stars. So many massive stars will evolve into black holes.
After sort of a supernova?
After supernova, indeed, that kind of thing. So given that we know a lot of binary stars, massive binary stars, we do expect a lot of binary black hole systems, two black holes orbiting each other. But they are expected to be separated very far away from each other. They are not expected to be easily merging, right? So the question again, now I think you maybe get to similarity with the planet problem. So we have these two black holes form out of binary normal binary stars, but they're far away from each other.
Yeah.
How do you get them so close so they can merge? Okay, so the trick in this paper we are doing with this, you mentioned this paper 2 years ago, where what we are saying is that you have two binary black holes, they're far away from each other. One way to bring them closer together is to imagine they are the third body, the tertiary body.
Yeah.
Far away, really far away. So even though the tertiary body is far away, its gravity is acting on the binary black hole. It can push them closer, put them in the elongated orbit. So that
over time.
Over a long time, yeah, indeed, right? and they can come close. And once they come closer together, sufficiently close, gravitational radiation can take over, can make them merge. So you see that that's why I'm saying these two papers have, even though it's very different topic, they actually have the similar kind of mechanics.
It is, yeah. And so this third body you're talking about, Dong, it doesn't have to be a black hole. It can be a neutron star or something like that.
It has to be, yeah, it can be neutron star, it can be other things, but you do have to be sufficiently strong.
Yeah.
Of course, if you have just a little tiny thing, of course, you do need a sufficient strong. There's some constraint. I mean, it's not arbitrarily small, clearly, right? But it's overall, it can be very far away. Okay, so these two black holes, for example, could be like 10 solar mass, 10 plus 10 solar mass. Each has 10 solar mass. The third body could be 10 solar mass, but could be hundreds of times away from this mutual separation. So you can see the effect, right? It's a very feeble effect, gravity. Yeah. But the gravity, as you probably know, it's very long-ranging. You cannot hide gravity. Right? You cannot shield it. Like electric force, magnetic force, you can protect it. Gravity is always there. It's always there, even though it's very far away. And then we also have time. The time helps, right? And over time, the gravity from this distant companion black hole, companion neutron star, companion thing, right? Tertiary body, it's pushing the inner orbit into elongated shape. They get very close.
So I want to understand this, Dong. So if we look at the Milky Way, we know there is a supermassive black hole at the center of it.
Mm-hmm.
I don't know the dimensionality. So what is sort of what's the distance from us to the center of the Milky Way?
Okay, it's about 8 kilopascals. So it's about 25,000 light years.
So 25,000 light years, and we know that we have supermassive black hole sitting there.
Yes.
Wouldn't it have effects on us? I mean, wouldn't it?
Excellent question. Yes. Yes. Yeah. This is one has to. Yeah. We have to calculate it, this thing. Yes, indeed. So when I say indeed, I mean, this is a very good question. That's why we need to. I cannot answer this sort of qualitatively, right? Because I just emphasized to you that in this black hole system, you have a very distant companion. Even though it's very feeble, it can do change the orbit, but you do have to be sufficiently. You cannot be infinitely far away.
Right.
If it's too far away, it's not going to be effective, right? I mean, it's going to be. You have to be sufficiently close. So it's like so.
About this triple system, we are talking about maybe a few thousand light years sort of separation.
No, not that far away. No. We're not talking about that. So we're talking about, for example, this binary, for example, the two black holes, 20 plus 20 solar mass. They may be separated by, let's say, 20 AU. So it could be the distance between the sun and the Jupiter. So they're pretty far away. And then the companion could be several hundred AU. So several hundred, several thousand AU. So it's it's not thousands of light years. Okay, so it's a matter of, that's why we need the mass to really quantify this kind of things. So it is far away compared to the separation. So if the separation is this, that guy, the tertiary companion, could be hundreds of times more distant than the separation. Right. So in that sense, it's pretty far away. But again, so even not be very far. If it's too far, then it's not going to be helpful. Of course, we're safe. I think our solar system is safe for the supermassive black hole at the center of the galaxy. If you do the calculation, it's completely fine. Okay.
You think they're safe till next election then? So hundreds of light years. So the process here you're saying is sort of similar.
Yeah.
The misalignment that we saw in the hot Jupiter systems, the process is somewhat similar. There is a third object that is sort of influencing the two
dynamics. Yes.
Is bringing the black holes together.
Indeed. Yes. Yeah.
And so I guess it's sort of a runaway system, right? When you bring it to some critical distance between the two, then they sort of take over, I would think, right?
Indeed, well, once you get closer enough, gravitational wave emission, it's efficient only when things, two big objects moving around each other sufficiently closely together. If they're too far away, they're very feeble. The gravitational wave is not going to be able to bring them together, right? So that's yeah, that's the way to think about it, right? So again, initially, these two black holes are far away. They don't do anything, but with the help of a distant tertiary companion, they become elongated orbit, become close enough for gravitational wave to become important, and then the gravitational wave then take over, make them merge, and that's one of the ways of making this black hole merger that have been detected, right? Now, this paper also discussed spin, spin orbit, right? This spin, no, has not been measured for the black hole, right? So for the black hole, well, I should back up a little bit, okay? So when LIGO detect this merging black hole binaries, they detect, just two thing merger, they can actually extract useful information from the merging system. They can get the masses of individual black hole, merging black hole. And sometimes they can also get information about the spin of the black hole, not whole information, because there's limited, very difficult measurement. They can get, in particular, they can get some idea about the spin orbit angle, some kind of the angle between the spin axis of individual black hole and the orbit of the binary black hole.
So when we look at LIGO data, we are sort of looking at, so we can see the shape is, I don't know the right term, but the shape of the merger
of the waveform, of the gravitational waveform. It's sort of waveform, the shape, how the waveform evolve in time. They can measure that kind of thing.
Allows us to sort of conjecture on the spin of the two black holes.
The spin sort of enter in a very subtle way. The spin in especially certain component. They cannot get the whole information. They can get the sort of the spin. Each black hole has a spin. The projection of the spin onto in the orbital axis. They can measure that component. Okay, so there's some limited information on that spin now. For some of the systems among the 50 that have been detected, and it's very interesting. So because some of these systems they find that projected spin, it's small. Means so you have a binary orbiting each other. The black hole may be spinning very fast, but when you project it, it's very small. That means it's actually maybe perpendicular. Maybe sort of maybe the spin axis is perpendicular to the orbital axis, if you can see what I'm saying, right? Again, you have this, just imagine this dumbbell. The binary is a dumbbell, right?
Yeah.
Orbiting each other, right? The dumbbell is rotating, right? And then each lobe has a little axis. But imagine this axis of the spin axis is actually perpendicular to this rotation of the dumbbell. It's perpendicular. So that means there's some kind of misalignment. The angle between the spin axis of the black hole and the orbital axis of the binary is misaligned. It's very tentative at this point. Of course, it's very tentative because it's a very difficult measurement, right? It's very tentative, but there's some indication that maybe misaligned.
So that goes into your hypothesis that there is a third body involved.
So that's sort of that's a possibility. I wouldn't say we're still early in this in understanding some of these things. Still we need more data, but it's certainly a possibility that one of the ways to bring two black holes together, right? And so I should, this is a very similar. Again, this is even though these two topics I talked about planets, hot Jupiter, and merging black hole. They're very different topic, but there's some underlying similar physics idea, actually quite similar. They're all having to do with, external body changing the orbital orientation of these inner bodies, right? So that's what we're doing in astrophysics with all kinds of things, the similar physical principle, but that actually can be applied to different situations. I should I should perhaps add this effect has a name. I'm talking about this effect of this this effect that external body changing the shape, orbital shape of the inner binary. It's called Lidov-Kozai effect. Lidov-Kozai effect. So Mikhail Lidov, it's a former Soviet Union planetary scientist. Kozai, it's a Japanese astronomer. So they discovered this effect in the 1960s. Now, in what context? It's very interesting. In 1960s, Lidov, I think they were. If you look at the paper, they were worrying about the safety of artificial satellite around the Earth.
Yeah.
So you have Earth has this satellite around the Earth, right? The artificial satellite, of course, are very close to the Earth. They usually move in perfect circular orbit.
Right. Right.
So they worry about, at that time there was a worry. They worried about what happened if this for some reason the orbit of the satellite become elongated, become eccentric. That would be very bad, right? Because it will crush onto the ground.
Yeah.
Right. So they were worried that the moon, even the moon, it's our moon, it's very small mass. They were worried that gravity of the moon will act on the orbit of the satellite.
It's still a binary system.
Well, the satellite around the around the Earth is a binary.
Yeah.
Right. The moon is a distant body orbiting around Earth. Right. So the Lidov at least was worried about, the moon's gravity. Maybe even though it's very weak, over time it will change the orbit shape of the satellite, making the satellite elongated orbit, and that the satellite will crush into the surface of the Earth. That would be very bad, right? So this is he discovered this effect, Lidov-Kozai effect, right? And Kozai studied also later. So that's the origin of this effect.
Is that a measurable effect?
Sorry?
Is that a measurable effect? Do we actually see that?
Well, fortunately, the satellite is safe. The moon's gravity is not strong enough to push the satellite. But they had to worry about it because was not obvious, right? Because in astronomy you have a lot of time. You want to this thing. You want to make sure this. The satellite can last tens of years, at least 5 years, 10 years, right? So at least for over this decades year time scale, it's pretty safe. The moon's gravity is not enough to push the satellite's orbit into very elongated shape, right? So that satellite is safe. But anyway, they discovered this effect, right? So that's why we are basically this different system with similar kind of ideas. Basically, we just need to rescale things, right?
Yeah. So they said they're worried about it, but the effect is not high enough for us to really worry about it. But you're applying the same ideas in the hot Jupiter systems as well as the black hole mergers.
Yes.
I want to go into a few of your recent papers.
Okay.
Technical, hopefully we can keep it.
Okay.
So one of them is circular chaos in white-dwarf planetary systems. So you say the overlap of nonlinear circular resonances in planetary drives chaotic circular evolution of test particles.
Okay.
Timescales of circular chaos can excite particles' eccentricity to a value near unity, leading to tidal interactions of collisions with the system's central star. So what do you mean by test particle here?
Okay. So let me go back up with the background. White dwarf, okay, so the end state of stellar evolution. So the sun, our sun, will eventually become white dwarf. No need to worry because it takes 5 billion years to go, so it's fine. But eventually, our sun will become white dwarf. So in the galaxy, there's a lot of dead stars that already become white dwarf. So the white dwarf, okay. Now, one of the puzzles in the recent years is that many white dwarfs, a large fraction of white dwarf, have this strange metals on the surface that have been detected. Now that metal, the composition of those metals is consistent with the composition of asteroid, of own solar system asteroid. So that sort of give a hint that maybe those metals, maybe those white come from asteroid. So the idea is that basically maybe a lot of white dwarf has some of they have been bombarded by asteroid-like materials over time.
Yeah.
Okay. So then the question is, white dwarf is very small things. How do you deliver this asteroid material? They're very far away. How do you deliver them into the white dwarf surface? It's not so easy, right? I mean, the asteroid is very far away. I mean, how can you do that thing, right? Yeah. So, okay, so that's where we are suggesting, right? So we imagine, let's say, okay, in the before the star become white dwarf, it's a normal star like the sun. The sun, of course, has the normal star has asteroid belt, a lot of rocks, materials, right? They are populating everywhere, and they also have the sun also have 2 or 3 planets, just like giant planet, just like our own solar system. Yeah. Okay? Now the star evolve, become white dwarf. Some fraction of those asteroid belts, material, rocky things remains. The giant planet remains. Okay, so then what's going to happen? Right, you have this asteroid belt. Right, they're far away from the white dwarf, and you have some giant planets also there, hanging around, moving happily around the white dwarf. So how do we want to deliver? The question is, how do you deliver this asteroid belt material, rocky bodies? Yeah, push them into the surface of the white dwarf. So again, we are using gravity. So here, what we're doing is using the gravity of the 2 giant planets. Okay, the gravity of 2 giant planets push the rocky bodies in the asteroid belt, push them into highly elongated orbit.
So this will be, in our case, will be like Jupiter and Saturn or something.
It will be like Jupiter, Saturn, like things, yeah, okay. And they push the thing, and then they make the gravity through the gravity of this Jupiter and Saturn, of the white dwarf, excite eccentricity, pushing the eccentricity of the asteroid in a very elongated orbit, and then if its eccentricity is large enough, sufficiently elongated, then the asteroid will be pushed into the surface of the white dwarf. Okay. Now the process, that will get technical, but rough is in the process how the gravity works. It's complicated because it's over a long time scale, right? But essentially, it's the gravity of these 2 giant planets acting on the body, the rocky body, right, pushing it into it. The rocky body behave like test mass. So when you ask what's the test mass, well, it's because the rocky body, the asteroid, has a mass that's much, much smaller than the giant planet. So for this problem, the rocky body is like test mass, right?
Yeah, so I guess I don't know much about this, Dong, but my understanding is that the sun will become a red giant first, right?
Indeed.
So it will blow off, I would imagine, Mercury, Earth, and Mars and stuff like that. So it will sort of clean up the space, right?
Yeah, clean up the inner solar system, but the outer one is okay. Jupiter is okay. Very good. Yeah, yes, you're absolutely right. The inner solar system, Mars, those things will be not, Mercury, they'll be cleaned out. But the asteroid belt, they're far away, and then the giant planet, they're safe, right? And so what we did in this paper is to work out the sort of in detailed way exactly under what condition the gravity from the 2 giant planets acting on the bodies in the asteroid belt can push the rocky body into very eccentric orbit and then contaminate the white dwarf. Okay, and the process it has to do with this chaotic dynamics, basically. So what happens is that it's 2 giant planets, they're orbiting each other, their motions are not very regular. They are. You need three giant planets. Two. They are not very regular. They're perturbing each other, right? And then the motion is not exactly circular, so they through some resonant interactions, chaotic motion, they can actually push the rocky body into the eccentric orbit. Okay, under some conditions.
What will be the diameter of the sun when it becomes a white dwarf? It'll be pretty small, I would think, right?
That's exactly right, right? So indeed, the white dwarf, when the sun becomes white dwarf, its radius will be like the Earth's radius.
Oh, wow. Okay.
So okay, so that is why you really need a very elongated orbit, right, to be able to push it, right? So it's actually not so easy,
It
right?
has to be precise. It has to be a precise projectile to get there.
Exactly. That's right. That's a very nice word. You need to aim it very precisely. So it's actually not so easy actually to do, right? And you need the special conditions. The two giant planets must be has some eccentricity. Cannot be perfectly circular orbit, and must have some mutual inclination. So not perfectly in the same plane, right? And yeah, the astral belt must also in certain region. Then you can do these things. Then you
Yeah.
can do this.
It's throwing darts.
Yes, so right. So there's tricky ways to to aim these things. Yes, you
Yeah.
need special conditions. So so this is one of the way to deliver sort of what we call delivered asteroid material into this white dwarf using the dynamical chaotic motion of the two giant planets, two or three giant planets.
Yeah, so I want to touch on a couple of other papers. So another one that you have coming out, giant planet scatterings and collisions, hydrodynamics, merger-ejection, branching ratio, and properties of the remnants.
Yeah.
Planetary systems with sufficiently small orbital spacings can experience planetary mergers and ejections.
Okay.
The branching ratio of mergers versus ejections depends sensitively on the treatment of planetary close encounters. So ejections here, planetary systems could essentially eject a planet right out into
Yes.
space.
Yes. So here we are dealing with the following problem, right? You have a star, yeah, two giant planets, both moving around the star. But if the separation is too close, if the two planets orbit are close to very similar orbit, then
Yeah.
the mutual interaction between the two giant planets can destroy the system in two ways. One of the way is that the bigger one will act on the small one, ejecting the small one. Small one will be kicked out, right? Another way is that they can come so close together, they collide with each other, right? Now, so these people work out the branching ratio, under what condition they will merge and what condition they will eject, right? So fortunately for the Jupiter and Saturn, our own solar system, they are sufficiently far away from each other. They're okay. Solar system is okay. Okay, a solar system is okay. They are the orbit is sufficiently far away from each other. They are safe, right? But
It's created by God after all, so it has to be perfect.
well, anyway, but what we learned from the study of exoplanetary systems over the last 2 decades is that there are many diverse kind of planetary systems that are very different from our own solar systems, right? And so this kind of thing can certainly happen. In fact, some of the exoplanetary systems, they have giant planets like Jupiter, but unlike our own Jupiter, the orbit are very elongated. You know, you know, it's actually quite strange.
Yeah.
In this picture I told you at the beginning, right? In the way we think about planet formation, everything's ordered. You have a sun, you have a disk, right? And everything when you form, everything should be quasi-circular orbit, ordered, right? And that's what we see in our own solar system. But in exoplanetary systems, planets outside the solar system, many giant planets have very elongated orbit, non-circular orbit. It's actually quite strange. It's actually quite strange why they are so elongated.
Yeah.
Right? Well, so one of the idea is that maybe not today we see only one planets around the star, but maybe before, early on, they actually had two or three planets.
And one of them.
One of them get kicked out. If that one of them get kicked out, what you see today is the leftover one. The leftover one having gone through this dynamical interactions with other currently ejected one, they become elongated, right? So that is the idea, right? That's the idea, right? And maybe the one we see today is the merger product of the previous two planets, right? And so
Is it fairly frequent, Dong, this ejection phenomenon? I was thinking, there were a lot of news about this thing that came from outside solar system. I don't know exactly how to pronounce it. Oumuamua.
Ah, okay. Yes.
Yeah. So is that something that could have been ejected by a system?
Indeed. Actually, yeah, the good point you're bringing up. Indeed, that could happen. Indeed, you have extrasolar planetary systems. They have giant planets. They have a lot of rocky things. It's certainly the case that a lot of the rocky things can be ejected by the giant planet of the other solar system. Yeah. They get ejected into interstellar space. So it's certainly true. This can happen quite frequently. Now, what is the probability that our own solar system capture one of these? It's difficult to evaluate because space is very big, right? There could be a lot of this junk, rocky things ejected from all over many different solar systems. Once in a while, one of these things will be captured into our own solar coming. So this Oumuamua certainly could be captured. Certainly, it's a leading hypothesis. Indeed.
So it's not an extraterrestrial craft or anything.
Yeah, some people, the book, written this. It's, I would say, the possibility, but it's not the most it's not the most conservative possibility, right? And I think there are conventional ways, as you just said, right? This scattering process can happen very frequently, indeed. Not only between two planets, but between planets and rocky body. They scatter, and then the rocky thing, the small one, unfortunately, get kicked out. Right. They're wandering in the space, and and they are very hard to observe until they happen to get captured in our own solar system, right?
The membership is cancelled by the big.
Indeed. So that is the more likely hypothesis. I think most conservative hypothesis for the Oumuamua, right, the visitor from the interstellar space.
And it might have been traveling for a very long period of time.
Indeed.
So radiation would have caused it to become a lot smaller, I would think, right?
If they happen to be close to one of the stars, yes. But in the interstellar space, they're pretty cold, so probably not. They may be, if they come to, if they pass to some other star too close, then they may be sort of diminished. That's certainly possible.
Right.
Yeah, indeed.
So I want to finish up with one of your other papers that are coming out, Jupiter's dynamical love number. Patients by the Juno spacecraft have revealed that the tidal love number of Jupiter is lower than the hydrostatic value. Present a sample calculation of the dynamical love number of Jupiter that explains observed anomalies. So what exactly is the love number? Okay,
the love number is Mr. Love, Professor Love. It's it's not a joke. It's a professor maybe 100 years ago in Oxford or Cambridge. Okay, he's the expert on elastic body. Elastic bodies. Okay, now what is love number? He was the one first investigated this kind of things. Okay, so what happened? It's in general. Okay, so in the case of Saturn, right? Jupiter, right? Jupiter, it's happily rotating, right? But Jupiter, of course, is orbited by several moons, Titan, some other things. Several moons, right? The moon, even though it's very small, it has gravity acting on Saturn, raise the tidal bulge on Saturn,
On Jupiter, you mean?
Sorry, on Jupiter. Sorry, yeah, right. The moon raised tidal bulge on Jupiter, so as a result, the Jupiter is no longer sort of has this tidal bulge, right? So it's distorted.
Yeah.
Now
It's not spherical anymore. It's sort
it's
of
not spherical anymore. Indeed, yes, not spherical. It's distorted. Now this distorted body will produce gravitational field. That's not so not just what you just like point sphere. It will be different from the gravity from the spherical body.
Yeah.
Right. Of course. Right. Because it's distorted. The gravitational field produced by the distorted Jupiter will be different from the spherical Jupiter. Okay. Now, this Juno is a satellite launched by NASA some years ago and come close to the Jupiter system. It's moving in that Jupiter system. It has a very precise way of measuring its own motion. So therefore, actually, even though the Jupiter's distortion by the moon's gravity is very, very small, Juno mission, the satellite spacecraft, was able to detect this very, very tiny deviation of gravity due to the distortion from the Jupiter.
Right.
Okay, so that detected that thing, and this love number essentially is a measure. It's a measurement. It's a measure of how big this distortion is, roughly speaking. Okay, how big the distortion is. Okay, so what was found is that when people can calculate the love number, of course, Newtonian gravity. It's not easy to calculate, but the general idea is simple, right? It's Newton's law, your fluid body distortion, calculated thing. People calculate it. It's found that this the measurement, there's some deviation. The Juno's measurement is somewhat different by 4% from the measurement from the theoretical calculation, the best theoretical calculation. Okay, 4% difference. Okay, so okay, what's the origin of that 4%? It turns out what we studied in this paper is that it's basically what happens is that this tidal bulge is not static. Usually we say, well, you have this moon's far away, raising a tidal bulge. It's sort of always, the bulge is always sort of sitting there, right? And right, it's a sort of it's a static feature. But what happens is that the moon is actually moving. It's actually moving, right? It's not the moon around the Saturn is not constant. It's actually moving, and also Jupiter. The Jupiter is also spinning by itself. So both of these things, the spinning motion of the Jupiter and the orbital motion of Saturn, that implies that the body. If you sit on Saturn, imagine yourself sitting on Saturn, you are going to see the moon is actually moving. So that means the tidal bulge is not static. Because you're seeing the moving body, the tidal bulge has to keep adjusting to the motion of the perturber, right? So it turns out that when you do this sort of subtle calculation, taking account of this motion of the moon, right, of Saturn, of Jupiter, you can actually, if you do that carefully, you can account for this subtle difference between the original static calculation and the measurement from Juno. Okay, so that's a sort of the little puzzle we solved basically.
So it's a dynamic system. I would imagine that Jupiter has many moons, so all of them are sort of affecting all of them are bulging up in different locations.
Indeed, that's a very good question. Yes, indeed, Jupiter has many different. Each moon has its own, give its own tidal bulge. So there are several different love numbers basically. Each moon has its own, give its own tidal bulge. Indeed, you're absolutely right. So
you have to somehow sort of come up with a way to combine them all. I was wondering, Dong, that do we have a precise measurement of the composition of Jupiter? Do we know the core, if there is a hard core for Jupiter and stuff like that? Or that's
very good question. So this would be yes, again, there's a lot of recent progress on this thanks to Juno, the Juno mission. Again, you have this spacecraft moving so close to the moon, to the Jupiter, right? And the spacecraft can measure its own motion extremely accurately. So it can, if you have mass, different kind of mass distribution inside Jupiter, they can probe it. Okay, so yeah, actually I don't work on this in great detail, but I just heard a talk recently. Yes, indeed, the Juno mission has revealed a lot of interesting internal structure of inside of Jupiter, right? So there is a big core, diffused core. The core is probably not very traditionally thinking it's sort of very concentrated, but rather diffused core. And there are some region which is sort of, we would call convective. Some region is stable. Convective means there's a lot of all this motion, and there's all this so-called differential rotation. So the whole body is rotating, but it's not precisely at the same rate. Different parts of Jupiter may rotate at a slightly different rate, and because of this differential rotation, they generate the distortion, rotational distortion, right? When you rotate the body is oblate. The rotational distortion can be different, and that can change the gravitational field produced by Jupiter, and that can be detected by Juno. So that have been detected. So from those detection, people can infer all these kind of things about internal composition, the size of the core, the rotation, differential rotation inside of Jupiter. Okay, and there's a lot of progress on this actually.
And we have that red spot going on there too, right? So that is hundreds of years.
That's hundreds of years. Yes.
Hundreds.
Yes. It's still somewhat that people think they understand it, but I don't understand it. It's quite non-trivial to understand yes, the atmosphere motion is quite a complicated thing. Yeah.
Yeah, excellent. Yeah, so there's a common theme running through all of this, which is when you observe phenomenon, sometimes there is a body out there that is actually creating the phenomenon.
Well, help you. Yes, indeed. One of the common themes all this I guess I talked about it. You could say, well, it's F equals ma, Newton's law. But you can see this F equals ma. We learned in sort of high school. They put in different context. They can play. Can do very different things, right? And sometimes very subtle way can do all kinds of tricks and creating variety of phenomena. So that's actually quite interesting. So ranging from planets to black holes. Okay.
Yeah. Excellent. Yeah, this has been great, Dong. Thanks so much for spending time with me.
Okay, great pleasure to talk about this thing. Thank you. See you.
Thank you.
Bye-bye.
Bye.